Morning, everyone. So today we're going to introduce a new chapter. This one here is going to be a chapter on organic chemistry. It very loosely has to do with when you go to the grocery store and you get organic vegetables. When we talk about organic chemistry, we basically mean pretty much the chemistry that's involving carbon. Right? So that's one way of just framing it here. Organic, it's the chemistry of carbon. It turns out a lot of our biological molecules, sugars, proteins, lipids, things like that, they're all based off of carbon. What makes carbon so special is the fact that carbon can actually bond to itself. So if you look at where it is on the periodic table here, carbon is group 14, so it has 4 valence electrons. Usually it is unpaired electrons that end up doing the bonding, while carbon has the capacity to actually make 4 of these attachments. As I just mentioned, carbon can actually bond to itself. So far, that's just a diatomic molecule. Well, even halogens can do that. Turns out this property of carbon being able to bond to itself can happen again and again. We can actually get a long backbone of carbon. We can get carbon end up forming little rings. We can get carbon and double bonds, right? So lots of variety. It gets really complicated really, really fast. My student teacher used to say, well, organic chemistry is the chemistry of chons. So basically, yep, you have carbon. You'll definitely see a lot of hydrogens, so hydrocarbons are very common. Sugars will tend to include more oxygens. There will be other elements as well. Our DNA will have nitrogen and sulfur compounds as well, but pretty much we're centered around carbon. Right? So just a brief introduction for this lesson here. Organic chemistry is a branch of chemistry that's related to the structure, composition, reactions. Primarily, it is going to be carbon and hydrogen, but it frequently does contain other elements as well. So this is TNT, used as an explosive. Trinitrotoluene here. Hopefully your pictures show up a little bit better. So this is actually based off a benzene ring. We talked about benzene having resonance. That's why we have this sort of electron delocalization. But if you take this TNT here, one very common reaction for organic chemistry is combustion. So reacting with some number of oxygens, we're okay with the odd fraction here or there. Maybe this is an enthalpy of combustion where TNT had to be a 1, and this one here has to burn. We assume combustions are complete. So therefore, a complete combustion will fully oxidize it to become CO2 and water. Because this chemical here does have a nitrogen source here, unsurprisingly, we end up having some nitrogen compound afterwards. But very, very exothermic here. It's going to give off a lot of energy to the outside. So in the early 20th century here, there was a common way of actually taking cotton as cellulose and actually changing it into a form that resembled TNT. And basically, our cellulose here, you'll notice that it has these OH groupings, whereas for our trinitrotoluene, we actually wanted N2O as well. So what we wanted to do is we wanted to find a way to systematically sort of swap in, instead of the OH, we wanted to swap in some NO2 groupings as well. This was later called gun cotton. Trinitrocellulose here, also explosive here, and this was a precursor to TNT. Right? So just introducing to you some organic compounds here. One interesting fact about this gun cotton here is even if you are underwater, it's so exothermic that it can actually be ignited. So this would be useful for like an underwater flare. All right, so it would be really useful. Gun cotton contains enough oxygen inside of itself that it can actually support combustion. You don't actually need to supply an external supply, although an excess oxygen from the outside would actually be good. What are some other everyday organic compounds here? So we have caffeine. Acetaminophen is the active ingredient for Tylenol. Aspirin, ibuprofen or Advil. Aspartame. Right, so this is a sugar substitute here. So a lot of the compounds that we deal with in everyday life is in the organic family. And as you can see, the organic structures will start getting complicated really, really fast. You need a systematic way of actually organizing and actually naming these molecules. So in this first little intro here, we're sort of getting our way towards this naming and introducing some common terms. So this first term here, a homologous series, super important. A homologous series implies that there are a family of compounds that something is the same about them. What's different is the certain common feature. So these are some things that you want to list for me here. Families that are a homologous series. They are successive compounds, they are increasingly large compounds, and the only difference is they start differing by a CH2 group. So for example, let's start off with methane. Methane is our simplest organic molecule, CH4. It's as simple as organic chemistry gets. Carbon has 4 unpaired electrons. It would be a radical right now. So what you need to do here with those unpaired electrons, the carbon would need to bond to 4 other H's, right? Well, what is the next biggest alkane? Well, we can actually go up to ethane. Ethane, we're going to actually take that same CH4, and all we're going to differ is we're going to differ it by one CH2 grouping. It's almost like one branch, and then now comes the other hydrogen there. So you see that all we've added on is a CH2 branch. Now it's ethane. Now it's a little bit bigger. We can continue that process here. We can get it up to propane. Well, propane here would have the CH3. It's going to have 2 of these CH2 successive units here. It's going to be even longer now, and now we're going to end up with just the hydrogen on the end. So that's propane. Let's do one more here with butane. All these are gaseous at room temperature, so they're useful for fuels. Combustion is a very common reaction for these ones here, but these ones so far are homologous series because all they differ by is just some number of the CH2 unit. In fact, we can actually say CH2 to the N, right? So basically you have something, and then you have this CH2, and then you have some number of this one, and then the rest of the molecule. So homologous series are chemicals that differ by just a CH2 unit. That actually gives you the general formula. These are all in the family called alkanes. We're going to see these later on in the lesson here. The general formula for an alkane, the general pattern that you see between how many carbons you have and how many hydrogens you have, pretty much we're going to use this idea. Every carbon at least have 2 H's, right? All these successor groupings have 2 H's. There's only 2 exceptions. The 2 carbons on the really end have 1 extra arm to hold hydrogen. So therefore, for an alkane, the general formula is Cn. We're going to double the number of carbons for the number of hydrogens, but we're going to add 2 for the terminal carbons. They actually have 1 extra arm. Basically, whatever's not implied is just hydrogen. So homologous series, first thing is they have to all differ by one CH2 unit, and they're going to get larger and larger. You can think about what that happens to the London forces. Members of the same family can be recognized by the same general formula, like I just mentioned, CnH2n plus 2. Usually the different organic families, we'll come back to in tomorrow's lesson to look at some functional groups here. Functional groups are specific groupings of atoms that actually allow the molecule to have specific properties. I'm not going to ask you to memorize a lot of these properties, but what we're going to find is because we're in a homologous series, to be in the same family together, we have to all have the same functional group. So, for example, let's take methanol. In our naming, we're going to see meth something just means 1 carbon. Methanol actually has a formula. It essentially is a methane molecule, but instead of an H, it's been substituted with an OH. That OH functionality actually puts us in the alcohol functionality, which is why we actually changed the name to methanol at the end. Well, how does ethanol differ? Well, ethanol had 1 more unit, so 1 more CH2, but it also has that very same functional group, and this one here is ethanol. Our drinking alcohol here is some derivation of this ethanol. We have propanol coming up next. Propane means something, there's 3 carbons, so we actually have 3 carbons involved. We have some of these more successive CH2 units here, but again, we have a similar OH functionality. That OH, it's going to allow for hydrogen bonding. That's going to give it very particular behaviors. You can even have butanol as well. This is a homologous series referred to as alcohols. Their general formula is a little bit different. So we have Cn, we have H. It is going to be 2N. But instead of just having everything as H, it also has 1 extra oxygen. So what we're going to do is we're going to say 2N plus 1, but we're going to leave the OH group together. You could have said 2N plus 2, but I want to actually identify, oh, OH is actually a specific grouping, and that actually fills in the next blank here. A functional group is a specific group of atoms, and that actually is responsible for giving this entire family very particular behavior. What else do we know about homologous series here? As these chains here steadily get longer and longer, they're going to show a small gradient in terms of their physical properties. It's a very regular succession. So let me just give you some numbers here if I just quote the boiling points. So methane, 164, negative 89 for ethane, propane is negative 42, butane is negative 0.5. So notice that by room temperature, these ones here have already boiled off. These ones here are gas at our regular everyday exposure, so 1 bar pressure. These are going to be gaseous. You need to be careful when you're working with those. As you get up to pentane, this one here is actually a liquid at room temperature because it takes a little bit hotter to actually boil off. Then 69, then 98, then 125. These ones here are actually liquids at room temperature, right? So if you do the energy option, a lot of these C5 to C10 or so are really useful for fuels because liquids are really easy to transport, a lot easier to actually manage. In fact, when we actually dig up oil out of the oil sands, we actually take crude oil. Crude oil is a big mix of a whole bunch of short chains and long chains, some gases, some liquids. What we're going to do is we're going to play with this trend of boiling point. We're going to have a heat source at the bottom of like a chimney stack here. This is going to vaporize all the gases. And what's going to happen is as the gases steadily get farther and farther away from the heat source, if I'm a relatively long chain, and I have a relatively higher boiling point, I'm going to be the one that liquefies first, and I can actually be tapered off. If I'm a shorter chain, I can get farther away from the heat source, I can get tapered off here, and basically what we're doing is by distillation, we're separating the different fractions based on the different boiling points. So going from smallest to biggest here, the increase in boiling point is due to having more carbons. Why does having more carbons imply more? In this case here, it's actually going to have increased number of temporary dipoles. And if you think about here in terms of van der Waals forces, we actually have stronger London forces as we end up having more charges. One indication of having more charges is having a much larger molecule. Okay, so for homologous series, they differ by a CH2 unit. They would, if they're in that same family, they have the same functional group, and they're going to show a gradation in physical properties. As the chain steadily gets longer, at least we see that the boiling point increases. Chemically, however, they're going to show very similar reactivities because the reactivity actually depends. Reactivity depends only on the valence electrons, on the outer structure. Okay, so most alcohols here have an OH functional group here that can be oxidized. We'll see that reaction later on into carboxylic acid. So I can convert an OH functionality to a COOH. We talked about this OH here actually having hydrogen bonding, but hydrogen bonding is typically more like a physical characteristic. Anytime we see the COH, we call it a carboxyl group. That group is a carboxylic acid, so it's actually acidic in nature, but it is going to be a weak acid. The Ka is actually going to be fairly tiny. So every time we see the COH, let's think back to our molecule CHQ. The CH3 is telling you how many hydrogens are actually bonded to that carbon on the left side. The Cu grouping actually implies the functionality. The COH always implies C, double bond O, single bond, like that. And anything that's not showed is a lone pair. Remember, for a Lewis picture, you have to have all the electrons. So far, the functionalities here, and OH is sort of the most reduced form here. Upon oxidation, upon having an oxidizing agent, we can somehow get it to convert into this COH grouping here. Okay, we're going to see in the upcoming classes here different functionalities and different reactivities for the different groupings. Okay, so on to the next slide here. As we start looking at different organic compounds, there's many ways we can actually represent them. So we can show the empirical structure, right? Empirical, we learned last year. This is the simplest whole number ratio. Not super useful for our organic chemistry because this is supposed to be an organic molecule. Organic may be multiples of empirical unit. Sometimes the simplifying isn't helpful. We actually want more so a molecular formula. I actually want to know how many atoms are in the compound. So let's just start from there here. Empirical formula, like I mentioned, unfortunately it's been simplified. So simplest whole number ratios in your compound. So for example, my compound may be butane. Butane is C4H10. That one there is actually a molecular formula because I'm actually telling you, well, there's 4 carbons and 10 hydrogens. So that one there is a molecular formula. Molecular formula is the actual number of atoms in your compound. And I just want to sort of allude to this here. Molecular formula is always going to be some multiple of your empirical unit. Right? The empirical unit here has been simplified, has been sort of scaled down. The empirical formula for this would actually just say C2H5. If I have 2 of those C2H5s, that gives me my entire compound. Both of these are in some sense trying to condense the structure, trying to make it a little bit shorter. We can do it sort of in all the detail here. This is called the structural formula. The structural formula, let's say I do have C4H10. What I want to show is I want to show basically every atom, show how every atom is bonded. So not only who's attached to whom, I want to know which one's a single bond, which one's a double bond, who's actually doing the bonding. This one here is very useful. Very useful for bonding, to show the different functionalities and everything. That's true, but it's still lacking, but it cannot show the 3D geometry. Right? That's when we actually need those wedges and the dashes here. That's when we get to stereochemistry. But let's just do full structural formula. C4H10 of my butane here is a little bit too condensed, so what we're going to do is we're going to draw it all in the detail. I would imply the carbons are actually all connected together, unless otherwise specified, assume that they're all single bonded. This is actually a saturated molecule. Basically, everything that I haven't showed you is now actually attached to hydrogen. How many hydrogens does that afford me here? We have 4 hydrogens on top. We have 4 hydrogens on the bottom. That's why we had doubled the carbon number. The 2 carbons that were terminal, that were on the ends of the molecule, actually have 2 extra hydrogens. There we go, C4H10. This is what we referred for this compound. It's fully saturated because it has the maximum number of attachments, maximum number of hydrogens. Okay? So, definitely the structural formula, it's implying I want to give you all the details. I want to show you all the little intricacies of the molecule. What we're going to want is usually something in between. Molecular formulas are useful if I'm just trying to find molar mass, or I just take 4 times 12.01, 10 times 1.01. Structural formulas are going to take up a lot of room here. A lot of these guys here just come along for the ride. I want to focus just on the most important bits. So what we're going to introduce here is somewhere in the middle, intermediary here, is actually called a condensed structural formula, or just condensed formula for short. These ones here are somewhere in the middle. All are good ways of representing these compounds. Condensed formula basically shortcuts some of it, but leaves some of it out. And what it's going to do here is it's going to shortcut all the hydrogens. I'm going to imply that the rest of them are saturated with hydrogen anyways. Why bother showing all the hydrogens? I'm just going to say here, well, this carbon on the left is holding 3 hydrogens. I could say CH3 like this. Sometimes they even show it to you as H3C, just to show you, okay, this carbon is on the left-hand side. What about this middle carbon here? Well, this middle carbon here is CH2. Even though I'm going to write the H's here, I know hydrogens have to be at the ends. Hydrogen is an incomplete octet. This one here has to be terminal. It has to be on the side. So even though I have CH2, before I get to the next CH2 here, I imply here that the carbon is connected to the next carbon, connected to the next carbon, and finally to the ch at the end. So we have CH3. And therefore we have slightly condensed formula here. You can even condense that a little bit more. You can even write that H3C, CH2. Because the middle 2 units are actually the same, I'm going to double that unit, and then we're going to have CH3. If the carbons are, this is the homologous series here, if it's a CH2, that means here this is sort of the middle of the chain. What if I had something like, just for comparison's sake, what if I had CH3, 3, CCl, okay? Well, what is that formula? Well, this time it's not a CH2 unit, so it's probably not going to be the middle of the chain. This time they're actually terminal, they're actually methyl groups, they're actually CH3s. So for this one main carbon, this carbon is actually holding to 3 terminal CH3s. So there's a CH3, here's a CH3, here's a CH3. You see that that CH3 is actually not mid-chain. And this one here happens to have another chlorine group. That's going to give it some functionalities. We'll get to it later on in this chapter. So condensed formula here, it sort of shortcuts the hydrogens. You can draw out the rest of the hydrogens for the structural formula. I'm going to introduce you one more here called the stereochemical formula. Stereo just actually refers to the geometry in 3D, and this is actually where we start indicating, showing the 3D position. So we saw this a little bit in our bonding chapter. We had needed, let's say, a tetrahedral. Hopefully you remember the bond angle is 109.7. We can use the wedge. Right? The wedge indicates to us that the wedge is actually out of the page. It's actually jumping off the page at me. Whereas if I have a dashed line, the dashed lines are actually going behind the page. This one here is the dash. And dash means into the page. We are going to get to some isomers in the coming classes here. Sometimes their only difference is whether they're on the wedge side or whether they're on the dash side. So let's just try it out for a few sample molecules here. Ethane, we're going to do the IUPAC nomenclature on the next side here. Eth actually refers to there being 2 carbons. The ANE tells you everything is single bonded. I'm going to give you the structure we drew it earlier. This is actually C2H6. That's your molecular formula. That's the actual number inside your compound. Well, that could be simplified. Well, that's just 2 CH3 units. CH3 is your empirical formula. Even more simplified, not super useful for this stuff. Condensed structure, again, it doesn't condense it so much so that all the carbons are actually compacted together. It actually leaves the carbons separate from each other. And that way, even though I still know the carbons are attached to each other, the rest of them are just saturated with hydrogens. I can just draw this out here. I can draw the 2 carbons as being bonded together. I know hydrogen with its incomplete octet has to always be terminal. Hydrogen should never be mid-compound. This one here is in the alkane family. It is in that homologous series. We saw a few like propane, butane for slightly longer ones. What about ethanoic acid? Ethanoic acid still has the eth, still tells you there's 2 carbons. We're going to see that by changing the ending. It actually tells you what family you're in. This oic acid is actually in the carboxylic acid family. Being in the carboxylic acid family here, the condensed structure here is actually Chiku. Right. So that one there is going to be your condensed structure formula, because it shows you why, well, there's actually 4 hydrogens. Why don't I just say, well, there's 2 carbons and 4 hydrogens and 2 oxygens. Turns out I want to just imply to you 3 of the hydrogens are connected to this 1 carbon, whereas the other hydrogen is actually connected to another oxygen. So the condensed structure actually helps you do that detail as well. Empirical, again, not super helpful. This would just be C1H2O1. I don't know when you would actually just need that empirical formula. But let's draw it out here. So we have CH3, that's carbon bonded to 3 H's. So those 3 H's are bonded to this carbon. We had seen the COH actually puts us in the carboxylic acid family. More on these families later on. Carboxyl or carboxylic acid, whenever you see a Cu, it means C double bond O, single bond O and H. We had seen this molecule here, not just memorizing, dilute samples, vinegar, things like that. This one here actually doesn't show resonance until you lose the H. In the acid-base chapter, when I lose that H+, yes, the electrons are delocalized, and that actually adds stability, and that actually makes it more favorable for losing that hydrogen there. Let's do one more here. This one will be quite horrendous here. Glucose is an example of a very simple sugar. The molecular structure is C6H12O6. That would be nice as a condensed formula, but again, condensed wants to show you some difference in terms of where the carbons are. So glucose actually ends up forming a ring. So I'm just going to draw it over here. So this is actually one other way of representing it here. We're going to have carbons as represented by the corners of the rings. This is actually called the skeletal structure. It's like the skeletons of the structure here. And what's going to happen is this is the carbons forming a ring. We're going to see that on one side there also is another carbon, and that's the last of the 6 groupings here. But there's a whole bunch of oxygens as well. That's sort of in the ring form. If it's in the non-ring form here, I can draw it like this. We're going to have 6 carbons, so 1, 2, 3, 4, 5, 6. If you do the biology option, biochemistry option, you could do all this. How do you open the ring and how do you close the ring here? For the time being, we're just going to practice. On the one side, we actually have an aldehyde functionality. Yes, you'll need to memorize these functionalities shortly. But we have that there. Every one of these carbons actually has an OH group. Depending on what form of glucose it's in, the OH may be on the same side or opposite sides here. That can differ. What I haven't shown you here could be a whole bunch of hydrogens. So what we could do, again, this is very scary, we could say, well, basically, a lot of these guys here have CH2O, okay, and I have a couple of them all in sort of one row there. I can start off from the top. We're going to use CHO to shorthand this CHO part. Then I have a bunch of these CHOH groupings. So CH and OH, I have 4 of them in a row, albeit, yes, the hydroxides, hydroxyl groups are on opposite sides. I have 4 of those, and then comes one last grouping here, that's CH2OH. that would be the condensed structure for glucose. Really, really scary. Probably a molecular formula might be useful. Okay, so there isn't one right way of representing it here. This one here with the empirical formula CH2O, similar as ethanoic acid, but totally different molecule. This is going to be a simple sugar. Okay. So just to sort of end off our introduction for today here, we are going to switch over into a little bit of the basics in naming. We're going to see a lot more with functional groups here in tomorrow's lesson. Organic nomenclature, not only do we categorize them into the different families, into the different homologous series, and find their general formulas, I actually want to be able to name the compounds. Remember, there's a group, it's an international group here called the International Union of Pure and Applied Chemists. So they're IUPAC. Sometimes they just say write the IUPAC name. It's basically name the compound using the system that I'm going to teach you right now. So organic molecules are named according to a systematic scheme as devised by IUPAC. IUPAC naming is the standard for all chemists, whether you're doing science in Europe or France or Brazil or Canada, wherever. Everyone will convert back to these names here. However, even though we do have a systematic IUPAC name, a lot of these names here have a common name. They have a sort of trade name as well, so you might need to know the common name as well. Right? So for example, if I take that molecule chiku, right, the IUPAC name would actually be ethanoic acid. Right? The ethane actually refers to the 2 carbons bit, but we've been calling this for the longest time, even in our acid-base chapter, we've been calling this one here acetic acid, based off acetate as an ion. So that's a common name as well. Let's do another one here. Let's do ethyne. So ethyne is actually the molecule HCCH like that. Well, wait, I would expect carbons would have way more hydrogens. In this case here, the carbons are actually triple bonded. I always count it this way. The carbon will always have the equivalent of 4 bonds because I've showed you 3 of the bonds are actually attached to each other. Each carbon only has 1 extra arm, and I'm going to assume the rest are hydrogen. So a common name, IUPAC name first, ethyne. That's the name I'm going to be giving it. This one here has a common name. We're going to call this one here acetylene. Okay. Unfortunately, here it does use that E-N-E ending. Usually we reserve the E-N-E ending here for a double bond. But again, that's a common name. There's a sort of analogy. Yeah, if you're learning to speak English here, you want to study the standard. You want to learn all the correct rules first, and then maybe some idioms and some slang names later on. They both refer to the same thing, but you want to be comfortable with both. I'll give you one more as a common solvent. This compound, H3C, we have a C. This is actually in the ketone functionality, as we'll see in tomorrow's class here. This guy, the IUPAC name, the standard name is supposed to be propanone, because prop refers to 3 carbons. This one here is an everyday name here called acetone, right? Used in a lot of nail polish removers, things like that. This one here is a polar compound, so it's going to remove other polar things. So just to finish off our introduction here, I'm going to introduce some of the simplest families first. I'm going to introduce the basic naming structure with these families, and then you can basically apply these rules to all the functional groups that we see tomorrow. Okay. So for starters, we're going to start off with alkanes. Alkanes are the simplest family here. The part that I'm focusing here on the A and E. Alkanes are compounds that only contain C's and H's. We have seen that name before. This is called a hydrocarbon. Right? Back in our stoichiometry chapter, we were burning hydrocarbons. They only had C's and H's. Where all the carbons are saturated, because saturated means it's completely packed full, everything is single bonds. Okay? So alkanes only contain C's and H's, and they're all single bonds. They're going to carry the suffix as the ending. Suffix is at the end of the name, so A-N-E, and the prefix, although 1 to 4 are a little bit weird, at least 5 to 10 are normal. 1 to 4, where we're used to saying mono, di, tri, tetra, that's going to come back somewhere else. We actually switch it up to become methyl, ethyl, propyl, butyl, or methane, ethane, propane, butane. I usually give myself a sentence, my elephant plays basketball, and that way you can know the 1 to 4 easy. So here's some examples. Oh, this is a single bonded structure. It has 2 carbons. Well, the prefix for 2 is eth, and we're going to just have the ending here, ethane. Right? What about this one? Looks a little bit weird. Well, how many carbons do we have? We have 2 carbons here. There's 3 hydrogens on all of them. Well, this here is also ethane, although it's just a slightly weirder way of looking at it. Going from 5 to 10, pentane, hexane, all the way up to decane, all that's normal. You can even have alkenes that are longer than it, but we're just going to go up to 10. We can draw one more here. So I have 5 carbons in a chain. Well, what's the prefix for 5? 5 is actually pentane. Pent is going to be the prefix. That tells you 5. Because we are in the alkane family, the suffix is going to be ane. This one here is also a pentane. I have 1, 2, 3, 4, 5 carbons in line, and that's actually going to form my parent chain. That's going to be the part of my naming system, and the rest of them are just hydrogens. Okay, so alkanes are the first family that we're seeing. Pretty much, we have the ane ending. What if I started swapping in a functionality? So let's swap in an alkene functionality. Alkenes are compounds that also only contain C's and H's, so hydrocarbons again, but at least they're going to contain a double bond. Don't just leave it like double bond. You want to say it's a double bond between carbons. Later on, you're going to get double bond to oxygen, double bond to other elements as well, but at least double bond to carbon makes you in the alkene family. Technically, you can have many different double bonds. For the molecules that we're going to do, they're only going to have one single, just one of them in the compound. So alkenes, because we're in the ene family, the suffix is going to end in ene instead. The location of the double bond is indicated by the numbering system, where the branches are occurring at the smallest number possible. So as you name this example, first thing that you're going to do, you're going to try to find the longest parent. I'm probably going to show you this on the next side as well. Find the longest carbon chain. So start from any side to any side. In total, I count 1, 2, 3, 4. What's the prefix for 4? The 4 is but. It would have been a butane had it not been for this double bond. The double bond, if I count it left to right, 1, 2, 3, 4, the double bond stretches between 2 and 3. Counting the other way similarly, 1, 2, 3, 4, also stretches between 2 and 3. I give you the lower of the two numbers. You'll either see this written here, but2-ene. That's the most common way. You can see it written 2-butene as well. Basically, the 2 tells you where the double bond starts from. It stretches from 2 over to 3. I'll write that down for you here. So the double bond, I know the double bond is between carbons for this functionality. Double bond starts from 2 to 3. And I just give you the lower of the two numbers. What if the chain was a little bit asymmetric here? What's the longest carbon chain? I have 5 carbons involved. Okay. If I count it left to right, the double bond stretches between 3 to 4. If I count it right to left, remember this molecule can be looked at from either side. Counting it from the other side would actually have the double bond between 2 and 3. So we'll prefer the 2 because that's the lower number. So this one here would be pent because I have 5 carbons in a row, and we're going to have pent 2-ene because the 2 tells you where the double bond starts. Again, you can call it 2-pentene if you like. We do that 2 there because we want to always keep the number at the lowest possible number. Keep the number as tiny as you can. If you count it the other way, it would be pent 3-ene. That's not as good. Last family I'm going to introduce for today here is an alkyne family. So far, these have all been hydrocarbon families, so they only contain C's and H's. But alkyne, you probably guessed it, alkynes will at least have one triple bond. We're going to simplify things a little bit. We're only going to have one triple bond between carbons. Okay. Later on, you may triple bond to nitrogen. That's a different functionality. But triple bond to carbon makes you in the alkyne family. Here, we're going to carry around the suffix and ending of a YNE ending. So we're going to be methyne, ethyne, and that's going to be the ending. And we're going to number it in the same way. So the numbers are tiny. In this case here, we have a 6-carbon parent. So we're looking at hexane. Right? And we're just going to change the ending to YNE because there's a double bond. Where should I count it from so the number is low? I actually want to count it, well, this one's symmetrical, so it's good between 3 and 4 no matter what I do. So hex 3-ine, if you like it. The other one, asymmetric here, is a little bit better. We have 4 carbons in a row. My elephant plays basketball, so but is my prefix. But, for carbon number 1, I want to count it this fashion, so the triple bond is at 1. If I count it the other way, it's stretched between 3 and 4. I would rather say but 1. But change the ending to YNE. Okay? So, let me add one last thing, and then we'll just introduce through the rules that we've been going through here. On the back side, the prefix, these guys here could actually end up forming a ring. They can end up forming a cyclic compound. So, if they are cyclic or they are a ring formation, we're just going to add the prefix cyclo. Cyclobutane, cyclopentane. And cyclo just reminds me that there's a ring. You still might need cyclo-1-butane or cyclo-2, depending on other substituents here. You may have other numbers as well. Okay. So let me just introduce you to the main way of doing IUPAC here. We're going to pick it up from here tomorrow. This is basically how IUPAC does naming. Okay? Especially important as you start doing branched compounds. Compounds containing only C's and H's, you can again call them hydrocarbons. Right. They're not always straight chains. They're not always in a flattened row here. Sometimes even misleading. It looks like everything is nicely 90 degrees. We know that from our VSEPR chapter here, if carbon has 4 electron domains, everything is actually tetrahedral. So everything is sort of kinked at 109.5. So more so, this one here should look something more like a zigzag backing and forth. For the skeletal structure, again, carbons actually end up forming the corners of this molecule. Really easy naming system. First thing you're going to do is find the longest carbon chain, and this one here is going to be the parent. Right? That's when you need your prefaces, methyl, ethyl, propyl, butyl, and all that. We're going to name any branches. So if I imagine the longest carbon chain as the trunk, and I have branches that sort of deviate from the branch, we're going to name these branches. The branches themselves are going to be called alkyl groups. They have a YL ending, so we're going to have the ending YL. So for example, I can have a methyl, or an ethyl, or a propyl, if that's a branch. If I have more than one branch, we're going to, let me add here, of the same branch, that's when we're going to start seeing the mono, di, tri, tetra come back again. If I have different branches, I'm going to want to list them alphabetically. Right? Lastly, we just saw if I have a multiple bond, the multiple bond here, multiple bond is so special, it gives you the functionality. The multiple bond actually takes priority. I don't care even if the other branches occur at higher numbers, the multiple bond is so special, the multiple bond actually takes the smallest number if it's present. Okay? So let's just work through a few examples. As I look through this first example here, first step, find the longest carbon chain. You can start from any side of the molecule and go to any side, but you can't double back on yourself. So let's say carbon, carbon, carbon. I have 3 carbons there. Well, that's not the longest chain. Why not go 1, 2, 3, 4, 5? It's not always going to be the left to right, but the nice thing about this IUPAC way of naming it is you're going to get the same name both ways. So just for simplicity here, sure, let's just go left to right. 5 carbons is the longest chain. That tells me I should be a pent. Because everything is single bonded, looks like all the carbons have all the attachments. Every carbon has the equivalent of 4 bonds. Everything has been saturated by the hydrogens that it needs. So we're in the pentane family. Pentane would have had all 5 carbons, everything is hydrogens. All we've done is, instead of where this arm here would have held a hydrogen, I've now substituted a branch. That branch here has 1 carbon in it. So this is a 1 carbon branch called a methyl. Where is that methyl branched off your parent? As I count my parent, I want to count so that the methyl branch occurs at the smaller number. If I count left to right, it's going to occur at 2. If I count right to left, it's going to occur at 4. So this one here would actually be 4-methyl pentane. It basically would have been a pentane, would have been 5 carbons all single bonded, but at position 2, it has a 1 carbon branch on top of it. The carbon branch has a YL ending. So let me just do a more complicated one here. Again, it's not always left to right here. This one is sneaky. They actually have it bent in on itself. The molecules are always freely rotating around single bonds that are twisting. In this case here, I have 1, 2, 3, 4, 5, 6 carbons in a chain. I would count it bottom up, 1, 2, 3, so my methyl branch occurs at a smaller number. You should be able to tell me here this is 3-methyl hexane. Right. I'll do one more with you here. Just takes practice here. Let's go from any side to any side. You should still find that 5 carbons is the longest one. You probably didn't do this 5, but you're still going to have the same name no matter which parent that you do. So I have 5, so that's going to be the very last word in the name. It's a pent. We're going to assume we're in the alkane family because nobody showed me there's a double bond or triple bond. Usually those ones here are sort of shown out more clearly. This time I have a bunch of methyl branches. I have 1 methyl branch, 2, 3, 4 methyl branches. They're all identical. Because I have 4 of the same branch, instead of calling it 2-methyl, 3-methyl, 3-methyl, 4-methyl, I'm just going to condense them all together. Let me just show you that step here. I would have called it here 2-methyl, and then 3-methyl, and then another 3-methyl, and then a 4-methyl. I'm going to condense all of that. Hey, I have 4 of the same group. I'm going to shorten all of that into a tetramethyl, but I'm still going to have all the numbers in front. One of them is at 2, there's 2 of them at 3, I still need to double the 3 because both of them are there, and then one of them is at 4. 2,3,3,4 tetramethylpentane, and that just sort of sums up that purple bit here. So just do a little bit of practice here. We'll pick it up from here tomorrow, and then we'll name some with functional groups. Thanks, guys.